This short tutorial on what is Make. So Make is a build tool. Make is a very simple program which will run certain commands when it is asked. It can also only run when a change of the files or the dependencies are done. So it can do incremental builds. So let's say you need to do task A, and for task A you need to do task B, and for that you need to do task C, which depends on, let's say, some file D. So Make will see if any changes are there from the previous build, and let's say the file D itself got changed, then it will do all the previous tasks first. So it will do task C, then task B, and then task A. So Make is smart that way, and it can actually do tasks and manage the dependency also. So Make is a very good tool for the dependency management of build steps. Where can Make be used? Make can be used in multiple places due to its versatile nature. It can obviously be used to compile code, so any code like C, Java, C++, etc., which needs a compilation step, that can be managed using the Make build tool. But because of its versatility, you can also use it for taking scheduled backups or for doing automation on pipelines. So let's see a short example of how Make works and how Make can be used to do repeated compilation of a C code. So assume you have some C code or any other language that needs compilation, and you have a big command to compile it, and you need to frequently compile it because you're working on the code and want to frequently see if your change in code has some change in the output. And you also have to do some dependency management. So you have to first delete the file, then you have to compile the file, and then you have to execute the compiled binary also. So let's see how we can do this. So let's say we have this one file which is hello.txt in our current directory. So let's open this file and see what we have in here. So this is a very simple program which first declares a variable called name, which is a string, and then it asks the user to enter their name, and then it stores that name which they enter into that variable. So pretty simple C code, and then it prints that name to the screen. So if we run this, we can run it using first compiling it. So we can compile with gcc oh hello, and then we can run this. So I can give my name, and I can see the output has come. So you can see that it's printing one extra new line to it. So this is because the input of my name also contained the new line, so that is also being printed. So when I am printing the new line here, that is printing another new line. So let me remove that and save, and now again I have to do the compilation step and then run the build file, and then I can again see the output. And here now if I want to, let's say, change something, so maybe I want to put a full stop at the end or exclamation after the hello, so then again I'll have to open the file and make the changes as required, save, do the compilation again, and then execute. So you can see it's a tedious process of writing a code, debugging some differences, and then again writing a code. So here you can see the dot actually came in the new line instead of coming beside it. So we have to also fix all these issues. So if I want to do this compilation and running step directly using some command, for this we use a Makefile. So here you can see in our current directory we have only the source code file and the executable file. Here we will also create a Makefile. So the Makefile should be either have a capital M or a small m, and everything else should be lowercase. So now you can see we have a Makefile. So we will open this Makefile, and here we will define what are the commands that we need to write. So here I can first define the command for running the build step. So I can say hello, which depends on the hello.c, and what this does is it does gcc hello.c oh hello. So this is the command which we are running, and you can see that we have given this hello here. So this means the name of the step is hello, and this step depends on the file hello.c. So whenever this file is changed, this will again run it. So you can see now if I do make hello, because name of our step was hello, so you can see hello is up to date. So it's not doing anything because the file has already been compiled. If I now remove the hello, then you can see that it is actually compiling again. So if I again run make hello, you can see it will not do anything. It will say hello is up to date. So if I then change the source code file also, so let's say I remove this dot which was not working. So if I remove it and save and exit, if I do make hello, Make is smart enough to understand that the file is changed, thus it has to run it again. So it will again run it. But if I again run, then it will not do anything. So Make is smart enough to not run the same command multiple times. This will save you a lot of time if your compilation process takes, let's say, a few minutes. So now here you can see we had to write make and then hello because that was the name of our target. But if I want to make that our default, then I can also use a target called all, and I can put hello there. So if I save now, and if I just run make, so you can see it is not running anything because the file is already there. But if I remove the executable and then I run make, then you can see it is doing the compilation. So as you can see, this process of removal also we might have to do sometimes. So instead of just writing remove hello, we can also put it in our Makefile. So we can add another target called clean, and what this will do is it will remove all the build files. So here it is simple enough that we only do it for one file, but if it's a big project, you can understand that there will be a lot of object files. So sometimes we will also not link it directly, but we will create separate object files and then we will do the linking process. So there will be a lot of .o files also. So to remove all the .o files, we usually use something like rm start.o. So it will automatically remove all the .o files. So here we just need to remove the hello, which is our binary. So now what we do is we change the file, which is hello.c, and whatever changes we want to make, we make and then save, and then we run make, and it will automatically compile the build file, and then we run it with /hello. So even this, you can see the running step, we have to physically type the name of the output binary. This can also be automated using the Makefile. So I can also create another target here, which will run the build file. So I can say run, which depends on hello, right? Because only after the compilation has been done can I run it. So run depends on hello. So as you can see, the dependency can either be a file or it can also be a target itself. So a target can also be a dependency of another target. So here we simply run the /hello. So here you can see if I just do make run, it will directly run our binary because we have not changed our file. So here I can say my name and it will print my name. Now here if I run make clean, so if you remember, make clean will remove the file. So now because the binary is not there, if I do make run, first make run will call the make for the hello. So it will do make hello and it will compile the hello and then it will do make run. So you can see the dependency management is done properly. So it will do a lazy running. So only if something is required to be done, it will be run. Otherwise it will skip ahead. And similarly, even if I don't remove the binary, but if I change the source code, so if I make some changes here and if I save it, so because now this dependency of this file has been updated, still if I run make run, it will first compile and then run the new thing. So usually we will not just use the name of the source and then -o name of the binary, but we will also use some flags. So something like -o2 for optimization, -g for adding the debugging messages inside the binary itself, etc. We can also give the standard. So standard equals C17. So all these is fine if I just write it here because it's just one file. But you can imagine if we have, let's say, 10 different files and 10 different targets, so writing the same thing 10 times will be very hectic. So that's why instead of doing this, what we do is we define a few variables in make. So we can define variables also in here, and I can say the C compiler which I use is GCC. So if tomorrow instead of GCC I want to use Clang, that is also possible. So let's change it to GCC for now. And we then define the C flags. So you can see the C flags which we want are W1, which means print all the warning messages, G for adding the debugging strings in the binary, and then O2 for optimization, and std equals C17. So now instead of using GCC, we will use the $cc. So this is similar to how bash works. So instead of using braces, we here use brackets. So $cc means it will use GCC, and then $C flags mean all these C flags will be put here. So now if I save this and if I now run make clean and then I do make run or just make, so you can see it is now using our full parameters of GCC to build this. So if you remember, the run depends on the hello and the hello depends on the hello.c. So if we have already compiled and if I run make run again, so it will not recompile. So you can see if I do make run, it is just running the executable and not compiling. But if I for some reason want to circumvent this behavior and I want make to always do the entire process even though it is updated, for that I can use something called PHONY. So I can say PHONY hello. So what this means is this will always treat as hello to be outdated. So if I run make run again, you can see hello is again done. So if I run it and then if I run it again, you can see even though the binary is already compiled and present and nothing is changed, still the hello target is always assumed to be outdated. So it is always doing the entire step of the way. So for some places this might be useful. So like here we have the file called hello and the target named hello, right? So when we are doing run hello, this dependency is on the file called hello, which is /hello, and not the target. But if I do PHONY hello, this means it will always actually do the entire process. So we can remove these for this one, but then this might be required in some other cases. Finally, let us see one last feature of the Makefile, which might come in handy when we want to actually print some things to the screen and we don't want to print some other things. So you can see if I do make run, so it's printing the step which it is doing. So it is running /hello, but it's also printing to the screen that it is running /hello. So if I don't want that to happen, I can go into the Makefile and I can add a @ before this. So what this means is don't print what you're doing to the screen, just do it. So now you can see if I do make run, this is not printed to the screen. So ideally that is not where we use it. So we actually want to see what commands are being run. So similarly for the GCC, when it is actually compiling, so if I do make hello, so here it's up to date, but then if I remove the hello and then I do make hello, so you can see we actually want to see the step that is happening. So we actually don't use the @ there. But if I want to print something to the screen, so for example before compilation, let's say I want to print now compiling the file. So if I now run this way, so if I run the hello and if I do make hello, so now you can see it's first printing the command itself, which is echo now compiling the file, and then the output now compiling the file. So for echoes we actually don't want to print the command because anyway the output will be there. So for echoes we usually always use the @ before the echo. So now you can see if I do make clean and I do make hello, so it will print the text but not the command used for printing the text. So that is how Makefiles work. If you want to see what are the processes that Make goes through while it's running, so if you run Make, so from the point of view pressing enter after typing Make and the point of Make finishing, what are all the things that Make does? How does it understand if some file has been changed and which parts of the dependency chain to be executed? So you can run Make with a -d flag. So this -d flag will print all the debug output. So this prints a lot of output. So you can see around 1200 lines of output. But when you're free, just try to go through these trace line by line and understand what is the Make process doing. So this way you will be able to understand even deeply how Make works. If you actually want to debug some issue with your Make and you don't want to go through that many lines of debug messages, what you can do is you can use the make -debug = b or basic. So let me first remove our hello file and then let me run Make. So now you can see GNU Make, only a few lines. So these are just a few license and copyright information. Then you can see it's reading make files, updating goal targets, file all does not exist, file hello does not exist. So right, it's working one by one. So must remake target hello. So it has now come to this conclusion that target hello needs to be done. Although we did not specify hello to Make, we just told Make. So by default Make goes to all, and then all, because depended on hello, it knows now it has to do hello. So then it runs hello. So you can see now compiling the file and the compilation step. And then this is again a debug message. So it tells us successfully remade the target file hello. So now it knows it can go back to the actual task it had to do, which is all. And then all, obviously because we don't have anything else in all, so it just says successfully remade the target file all. So you can see this is how Make works. Similarly, if I want to run for the run, so let me remove the file again, and now let me run Make with run. So if I want to run the run, so it will first see that run target does not exist, then hello does not exist because we deleted it. So it will remake the hello, then it will run that, and then it will run the target run. So now you can see we're inside the run and it's running the file. So then I can give my name, and then it will print the output, and then successfully remade the target file run. So this is how Make works internally. So let us see now an actual Makefile used in an actual piece of C code put in the deployment. So we are right now in a folder of DWM. So what is this project? So this is DWM, which is the dynamic window manager which I am using. So you can see whenever I am opening a new window, it is automatically being tiled. So this is managed by DWM, and wherever which window should be placed, how to place and how to resize and everything, that is managed by DWM. So you can see this is a pretty big project and it's around 84 KB of source code itself. So if I open dwm.c, you can see that the file itself has around 3000 lines. So this file also has a Makefile, and almost all C projects have a Makefile. So the Makefile helps us to understand which commands to run to build the project. So let us see the Makefile now. So you can see the Makefile of this project. So the first few lines are starting with the hash, so they are comments and they're ignored. After that, you can see there's an include file. So in Make also we can split the Make configuration into multiple files, and we can also include the files one by one. So here the entire Make document is there, and some variables are defined in some other file called config.mk to make it easier to configure only some variables. So you can see if we open that config.mk, then you can see only variables are defined here. So things like the version, the prefix, the man prefix, etc. So the C flags which we saw earlier, C flags and CPP flags, they're defined here. And the LD flags are also defined here. So these are the flags for the linking. And the C compiler is set to CC here. So whatever is the symlink of CC, that is used as the C compiler. So then you can see the variables which are being declared. So it's telling src as drw.c, dwm.c and util.c. So these are the three C source code files which are stored as an array in the src. And similarly, the obj are stored. So obj are the object files. So the object files are stored, so they are nothing but the source files, and then instead of the .c we are putting .o. So this kind of substitution is also possible in make files. So we are referring to the src, and for all the values of the src we are substituting the .c with .o. So then we have this all target. So when we just run make without specifying any target, the all target will be run. So what this all target will do is it will run the DWM target. So let us see what is the DWM target. So the DWM target will depend on all the object files to be present. So if some object file is not present, then first that object file will need to be created. So you can see how all the object files are created. So all the object files, they depend on the config.h and config.mk. So the config.h, then how to build that? So that is done by copying the config.def.h to the config.h. So this way you can see a lot of dependencies are managed. And then any .c.o, it will use the C compiler using the C flags. And we can run make options to actually see which options are present. So the DWM, if all the object files are present, it will use the C compiler to create the binary, which is the DWM binary. So it will link all the object files, and it will also use the LD flags. So the LD flags are the flags of the linking or the linker. So the C flags are for the compilation flags, whereas the LD flags are for the linker. So you can see it will use the linker flags, not the compilation flags, because here we are linking all the object files. Similarly, we have a clean target here, which will simply just remove the DWM executable and all the other object files, and also some zip files if there are any. And it will also remove this config.h. So the config.h is always copied from the config.def.h, and whenever we clean, it is again removed. And we also have a few like automation scripts. So you can see the dist or the distributable. So this is the step that will first, it will clean everything. So you can see it will call the clean one if it's not done. So it will remove all these files. Then it will copy all the non-code files like license, makefile, readme file, etc. And then it will tar them, and then it will gzip them. So you can see you can also combine make with tar and gzip to do things like backups, and in this case we are using it to create distributable. So it will take all of these and then put it in a folder, and that folder will be compressed and gzip. So this depends on the version of that DWM. So you can also use the version number using a variable. Similarly, we have a target for install. So if you don't want to create a distributable for someone else but want to actually install it for yourself, then it will run these commands. So it will first remove the files, and then it will create a folder called bin, and it will copy all these in that bin, and it will also copy your man page. So you can see the man page will also be created, and it will also substitute that version information in the man page. And finally, the permissions will also be set for that, and the other files created in the process will then be removed. So similar to the install, we also have uninstall, which will simply remove the binaries and the man pages which were added. And you can see here we have the PHONY, where all these processes are, or the targets are mentioned as PHONY, so they will always do all these steps instead of doing partially. So let's see this in action. So here, as you can see, I have the distributable here, which is this dwm/version.tar.gz. If I do make clean, then it will remove that. So you can see all that is removed. and now we don't have that anymore. And now if I do make test, so you can see all these steps are being followed. So first it's removing anything if it's there, then it's creating this folder, and then it's moving all these files in that folder, and then tarring it and zipping it, and then again deleting that folder. But now you can see this zip file has again been created, gzip file. So I can also use make clean to remove this, and I can use make install to install it. So the make install will not work because for installing it into our system we also need super user privileges. So I have to use sudo make install. So now you can see it will compile all the source code files, link them, and then also it will create the man pages. So now if I do man dwm, you can see the man page is also created there. So finally, I'll leave you with a few resources. So there's a really nice video by Gabriel Palmer on YouTube about Makefiles, and 95% of what you need to know. So you can go through this one to make yourself even more aware about Makefiles. And obviously you can go through the documentation of Make itself. So documentation of any tool or any language is always the best place to learn about that. So you can go through the GNU Make documentation. Thank you.